We are drawn to the universe's most mysterious horizons, and it is time that remains one of the most difficult questions for science, pursued by the greatest minds, among whom Stephen Hawking became the most brilliant researcher of our era. Stephen Hawking is one of the brightest figures in the study of the nature of time, the cosmos, and the structure of the universe. His life was an example of astonishing strength of spirit and scientific genius, for despite a severe motor neuron disease, he managed to make a fundamental contribution to the theory of black holes and cosmology. In the 20th century, he repeatedly made us doubt the immutability of time, transforming it from a linear arrow into a flexible fabric. Hawking popularized the idea of the irreversibility of time through the concept of entropy. Based on the second law of thermodynamics, he explained that time is linked to the increase of entropy, a measure of disorder in a system. An example is the melting of ice. Ice melts, turning into water, and this process cannot be reversed under ordinary conditions, symbolizing the irreversibility of time that we experience daily. In his works, such as A Brief History of Time, he explained why the past and the future are different and why the arrow of time points in that particular direction. One of his most significant achievements was the proof of the link between black holes and temperature, later called Hawking radiation. This meant that black holes are not eternal, but gradually evaporate, losing mass and energy. Thus, his research showed that time near black holes exhibits unique properties related to the rate of its flow and the loss of information, a topic still discussed today in the scientific community. Hawking also proposed ideas about the concept of the initial moment of the universe, the singularity, where classical laws of physics disappear and time itself loses meaning. In collaboration with James Hartle, he proposed the no-boundary universe hypothesis, where time has no beginning as such, and part of space-time is infinitely curved, like the surface of a sphere. This helps us understand time not as a straight line, but as a closed continuum. In the story of his life, there is an inspiring moment when, after receiving a diagnosis predicting a short life, he continued to work and create theories that changed modern physics. His example proves that the study of time is not only about formulas and equations, but also about human resilience and curiosity. Imagine that time is not a stream, but a labyrinth of mysterious corridors. Such an image of modern science is offered by Einstein's theory of relativity, where time stretches and compresses like strings in the orchestra of the cosmos. Albert Einstein himself made a revolutionary contribution to the understanding of time and space. His theory of relativity, published at the beginning of the last century, overturned conceptions of the cosmos, describing space and time as a single four-dimensional continuum. And although in popular culture, time travel often appears as science fiction, scientists have found real foundations upon which such a possibility could rest. Equally important is the contribution of Kurt Gödel, who in the 1930s proposed proof of the existence of closed timelines, allowing a return to one's own past. Gödel, a remarkable logician with profound philosophical views, showed that within general relativity, the idea of time travel does not contradict the laws of physics. This unexpected fact adds drama to the story. The boundaries of the impossible expand as we deepen our knowledge of the cosmos. In the 21st century, attention has been drawn to Kip Thorne, an American physicist and one of the pioneers in the study of gravitational waves. In his book, he describes tunnels in space-time that might be used as time machines. It was Thorne who helped create a theoretical model of the so-called wormholes, bridges stretching across curved space that could theoretically connect different points in time. Modern experiments are nearly approaching the testing of such ideas, though practical realization is still impossible due to numerous physical limitations, including energy and stability problems. Imagine a road through the labyrinth of the world, where every fork is a potential window into the past or future. Studies of wormholes, or so-called Einstein-Rosen bridges, are based on attempts to understand how different points of space-time might be connected through curved structures. Kip Thorne, one of the leading researchers in this field, together with his colleagues, developed a theoretical model of a wormhole governed by the laws of Einstein's general theory of relativity. Their work showed that such tunnels could exist in principle, but to stabilize them would require special exotic matter with negative energy, something not yet found in nature. Modern experiments focus on indirectly confirming such hypotheses by studying extreme gravitational phenomena, such as black hole mergers and gravitational waves. Observatories like LIGO and Virgo have become revolutionary instruments, allowing the first detection of gravitational waves, ripples in the fabric of space-time that may contain information about how space behaves under extreme conditions. Although wormholes have not yet been directly observed, these experiments make it possible to test the validity of theories about the curvature of space and physical conditions at the edges of such structures. Leading research groups work at universities and institutes in the US, Europe, and Japan, for example, at Caltech, MIT, and the Institute for Theoretical Physics in Lucerne. They use complex computer simulations based on equations from general relativity and quantum mechanics to model the behavior of matter and energy around potential wormholes. One of the challenges remains the recreation of conditions for exotic matter, a hypothetical substance with negative energy that has not yet been created or discovered in laboratory conditions. Recent progress lies in the fact that theoretical models and computer simulations show the possibility of stable space-time tunnels under certain conditions. Practical realization, including the creation and control of such structures, remains a distant prospect due to the enormous energy requirements and unavailable technologies. These studies demonstrate significant progress in understanding fundamental physics, bringing us closer to unlocking the nature of space and time. If the scale and depth of this research fascinate you, subscribe to the channel, like this video, and tell us in the comments what questions about time travel and wormholes you would like to discuss. Together, we continue the journey to the universe's most mysterious secrets. Quantum mechanics also brings its own mysteries into this picture. Scientists such as Richard Feynman discovered that particles can simultaneously follow multiple trajectories, weaving a complex pattern of probabilities. In this context, space and time cease to be immutable backgrounds of events and become a fabric that can be bent. Modern research shows that quantum fluctuations near black holes can create effects that resemble time loops. And although these phenomena are far from controllable time travel, their study brings us closer to understanding the deep laws of nature. At the heart of these studies lies the question that troubles not only physicists, but also philosophers. Does an unambiguous past and possible future exist, or is everything together a single multidimensional space of events? The world-famous philosopher and logician David Lewis proposed the hypothesis of multiple worlds, where alternative versions of events exist in parallel. In this context, time travel does not change the past, but opens gates into another temporal flow. Such an idea not only expands our concept of reality, but also makes us reflect on humanity's place in the universe. Interwoven with the narrative of research and experiments, we realize that the mystery of time is not only a scientific problem, but also a profound challenge to our consciousness, a call to continued exploration and discovery. Certainly, here is the continuation of the translation from Carlo Rovelli's section onward, maintaining the same faithful and detailed style. Delving deeper into the study of time, we cannot overlook the contribution of Carlo Rovelli, an outstanding Italian physicist and philosopher whose ideas are changing our understanding of the nature of time. Rovelli, one of the founders of loop quantum gravity theory, offers a unique perspective in which time ceases to be a fundamental quantity. In his view, time arises not as a separate entity, but as a sequence of relations between events. This work allows one to mentally free oneself from the habitual view of time as a constant flow and see it as a network of interactions in the complex web of the cosmos. For Rovelli, the past, present, and future are coordinates dependent on the observer, similar to how heat or cold exist only in the perception of the one who feels them. An important part of Rovelli's discoveries is his book, The Order of Time, where he applies rigorous mathematical methods to demonstrate that time can emerge from more fundamental phenomena. This approach is often called revolutionary, as it blurs the boundaries between physics and philosophy. Essentially, Rovelli invites us to go beyond the usual categories of time and see it as a living organism that breathes and changes along with the universe. His scientific works and public lectures continue to inspire physicists and philosophers alike, stimulating new hypotheses and experiments. It is interesting how Rovelli's biography intertwines with his research. Born in Bologna in the mid-last century, he studied physics at prestigious European universities and collaborated with the Institute for Advanced Study in Princeton, where he had the honor to work under the guidance of great minds such as Edward Witten. Rovelli is not only a scientist, but also a talented writer capable of explaining the complex in simple words, which is especially valuable for popularizing science. In an era when closed time systems and time travel through centuries seem like distant fantasies, scientists like Rovelli demonstrate that understanding time may be the key to solving the most fundamental mysteries of the universe. Their work is an invitation for discussion and reflection, which is valuable for all of us to continue. If you are interested in exploring the mysteries of time together with us, subscribe to the channel and leave a comment to share your thoughts. This will support the quest for knowledge and give impetus to new discoveries. Moving now to the figure of Kurt Gödel, whose name gave rise not only to mathematical logic, but also paved the way for scientific research on temporal paradoxes. In a grand partnership with Albert Einstein at the Institute for Advanced Study in Princeton, Gödel proposed a mathematical model in which closed time loops are possible. This means that an object can return to its own past, an idea that once seemed like fantasy suddenly gained rigorous foundations. Born in the 20th century in Austria, Gödel proved to be a brilliant mind from an early age, and his incompleteness theorems became the foundation of modern logic. However, it is his cosmological models that attract the attention of researchers interested in time travel. Thoughtful and deeply philosophical, he considered these possibilities not as tricks, but logical consequences of relativity theory. In his famous 1949 study, Gödel proved that if the universe rotates, then time loops could exist, and even the concept of time in the usual sense loses its strict meaning. Although observations show that our universe does not rotate in this way, Gödel's hypothesis symbolizes the boundary between theory and a potentially real world, serving as a foundation for further assumptions and encouraging experimenters to seek answers to questions about the nature of time. His thought took the form of a philosophical invitation, opening doors to alternative worlds and forcing a reconsideration of immutable axioms. Such an unconventional model can be compared to an endless labyrinth where temporal corridors lead not only forward but also backward. It is easy to get lost in it if you do not join the exploration with us. When we talk about time travel, one cannot fail to mention the many worlds interpretation proposed by Hugh Everett at the end of the last century. Everett, a young American physicist, challenged the classical view of quantum mechanics with his assumption that all possible outcomes of quantum events are realized in parallel universes branching infinitely and coexisting. His work not only changed the understanding of quantum theory, but also sparked the imagination of time researchers like nothing else. If every choice creates a new branch of reality, then time travel does not change the past but creates alternative lines of events. Imagine a vast, tree-like cosmos where every moment splits into many branches stretching in all directions. A complex, diverse space of possibilities and variance. Everett himself, brought up in a scientific family, showed an early deep interest in philosophy and mathematics, which helped him systematize and present his theory with exquisite logic. Unfortunately, his ideas were not widely accepted at first, but over time, their weight and influence grew, and now they form the basis of modern research in quantum informatics and computation theory. This view forces us to think about the possibility that time travel might mean traveling between parallel world branches. And though practical possibilities remain speculative, the idea expands the horizons of thinking and scientific inquiry. If such concepts interest you, subscribe to the channel and share your thoughts in the comments. Together, we will advance toward unraveling the great mystery of time. Let us again draw attention to the research of Kip Thorne, a Nobel laureate and one of the main champions of wormhole ideas, beloved by science fiction and simultaneously supported by serious mathematics. Thorne, an American physicist, devoted much of his career to studying phenomena of curved space-time and possible bridges connecting different points of both space and time. Mid-last century, alongside work on gravitational waves, Thorne popularized the idea that wormholes could serve as shortcuts through the cosmos and, in theory, allow time travel. He clearly warned of technical and energy obstacles, yet his mathematical models proved that these constructions do not contradict the fundamental laws of physics. In one of his interviews, Thorne noted that reality could hide thousands of such tunnels, but stable use would require exotic matter with negative energy, so far only a hypothetical substance. Thorne grew up in the USA, developing an interest in physics in school. His lectures and books made science accessible to thousands of listeners and readers, blending rigorous calculation with the beauty of the cosmos. His contribution inspired not only scientists, but also filmmakers. He was a consultant for the film Interstellar, which faithfully conveyed the complexity and potential of these scientific ideas. Thorne demonstrates that time travel is possible not only in fantastic scenarios, but as a result of deep understanding of the laws of nature. Such a union of facts and imagination awakens interest and a desire to learn more. If this captivates you, like this video and write in the comments which aspects of wormholes or gravitational theories raise questions for you. Together, we explore the mysteries of time and space. It turns out time travel has already begun to manifest in our technological reality, albeit on very small scales for now. On GPS satellites, time flows differently than on Earth because they move at high speed and are far from the center of gravity, where gravity is weaker. Researchers have discovered that atomic clocks on a satellite run about 38 microseconds faster per day compared to identical clocks on Earth's surface. This is a small shift, but ignoring it would cause navigation systems to err by many kilometers in just one day. Therefore, scientists have had to initially adjust the frequency of satellite clocks to compensate for relativistic effects predicted by Einstein's theory of relativity. And although these satellites do not fly very far, gravity's influence there is noticeably less, and the time difference is not a theoretical experiment, but an absolutely real fact that must always be taken into account for technology to work accurately. If a person spends a year on a satellite, then due to the slowing and speeding of time caused by gravity and speed differences, Earth time will be slightly detached from satellite time. And if a person stays in orbit exactly 1 year, more than 1/100th of a second will have passed on Earth. For everyday life, this difference is imperceptible, but for modern technology and navigation, it is important and always accounted for in time and coordinate calculations. Continuing the discussion of the nature of time, modern physicists repeatedly encounter paradoxes and unexpected discoveries that change our perception of this mysterious category. Recent research published in 2025 confirms that in many cases time may not flow exclusively forward, as we have been used to thinking, but shows symmetrical movement. That is, it can move both backward and forward simultaneously. This conclusion is based on observations of quantum systems where the equations of physics remain unchanged regardless of the time direction. Such symmetry defines a complex structure of time, shifting the boundaries between reality and illusion. One of the key concepts is the appearance of the so-called time break factor, which interrupts the smooth flow of events and introduces discreteness into the course of time. This detail, discovered in the equations, helps explain how systems can show reverse time flow at the quantum level, which at the macro level is still perceived as fantasy. The point is that our perceptions and experience form a one-sided view, but the fundamental laws of the universe are much more complex and richer than they seem at first glance. The time break factor is a concept that can be explained by a simple everyday example. Imagine a situation where time in some process suddenly stops flowing in the usual way, as if a jump or break appears in the temporal sequence. This does not mean that clocks stop. Rather, a sharp change of system characteristics occurs related to a change of the medium or object state. In physics, such a break is often described as a moment when system parameters change abruptly, creating a boundary between two different time intervals or states. For better understanding, one can recall how water behavior changes abruptly when temperature jumps and steam appears, a transition from one state to another. Similarly, in dynamic processes, the time break factor denotes a sharp transition between two phases, requiring a special approach for description. In theory, this factor helps model situations when time flow is interrupted and then resumes with different properties. In quantum mechanics or in the study of extreme cosmic phenomena, for example, near black holes, such effects are critically important for forming a holistic picture. Such a break cannot be maintained long without changing the equations describing the processes. It immediately decays into more stable structures. This helps scientists understand that time and events do not always proceed smoothly, but are accompanied by jumps affecting the course and development of events in the universe. It is precisely the study of such factors that allows progress in understanding the nature of time and possible time travel, since any time machines, if they exist, must take these jumps or discreteness into account. Simply put, the time break factor is the moment when the usual flow of time is interrupted and the system moves into a state with new temporal characteristics. This scientific tool helps physicists describe complex phenomena where time looks not like a smooth flow, but as a series of jumps and changes. It is important that by understanding and studying these moments, scientists come closer to solving one of the greatest mysteries of our universe: what time really is. Moreover, the idea that time may be an illusion is increasingly supported by the scientific community. Modern theories of quantum gravity and cosmology suggest that the concept of now is relative and individual, and what we call the present may not be an objective reality at all. This is also confirmed by neurophysiologist Dean Buonamano, who argues that our brain perceives time with its own limitations, and therefore many aspects of time escape our understanding. This view opens new possibilities for researching the interaction of consciousness and space-time. Another important direction is the study of the so-called block universe, a concept in which past, present, and future exist simultaneously. But we, as observers, can perceive only one point in this continuous flow. This idea is supported both by relativity theory and results of modern quantum experiments, bringing physics and philosophy closer in the attempt to explain what time is. It makes us ponder free will, causality, and the interconnection of all events in the universe. Imagine that our entire life is not a continuous stream, but a fixed whole film, where each scene, each event, past, present, and future, exists simultaneously. Such a marvelous picture is offered by the block universe concept, based on ideas of the German mathematician Hermann Minkowski, who at the beginning of the 20th century united time and space into a single four-dimensional space-time. According to this theory, the entire universe is a motionless four-dimensional block in which all moments in time are equally real and significant. To imagine this idea, a DVD disc is often used as a metaphor. The film on the disc exists fully, from beginning to end, yet we experience its scenes sequentially. Like a running strip, our perception of time is formed so that we pass through the frames one by one. However, in reality, all these frames, past, present, and future, exist simultaneously inside the entire structure of space-time. Scientists from Stanford University in their research confirm that the event we perceive as now is merely a point inside this large block, and no event is more real or unreal than another, regardless of whether it seems to us past or future. This changes our usual understanding of time, according to which the past has already passed and the future has not yet come. Understanding the magnitude of this discovery is helped by a simple analogy. When you watch a movie, you cannot change already played scenes, although they exist on the disc together with scenes yet unwatched. Likewise, according to the block universe concept, all events are already recorded and exist simultaneously, and we merely experience them in our consciousness, sequentially moving from one moment to another. This idea raises many philosophical and scientific questions. For example, how real is our free will if everything already exists in a single block? The block universe theory was supplemented by the growing block concept, where the past and present exist but the future is not yet recorded and is formed in the process. However, it is classical eternalism, the idea of a motionless block of all space-time, that opens science to an astonishing view of the existence of time. It makes us think that perhaps we do not move through time, but time itself is motionless, and our experience of movement is merely perception. In light of these discoveries, questions about time travel take on a new shade. If time is non-linear and multifaceted, perhaps the future and past are closer to each other than we thought. This is not just science fiction, but the result of serious research that may one day lead to breakthroughs in understanding the cosmos and our place in it. If this incredible path of research has captured your imagination, subscribe to the channel, like this video, and be sure to share in the comments which aspects of the nature of time seem to you the most mysterious and important for humanity. Together, we continue to open the great journey into the essence of time.